All right, in our multiple regression, I've given you guys another output, and our research scenario is looking at a random sample of 323 high school seniors, and students reported the average amount of time they studied per week in hours and the average amount of sleep they got per night for 2 weeks leading up to the exam. The English and writing sections of the placement exam were scored out of 100 points. A college admissions department wants to know if the amount of sleep and study time as well as English test score are sufficient in predicting a student's writing score. So, because the predicted variable in this case is the writing test score, and we have a prediction, we know we're looking at a regression. Test score would be our dependent variable, and then amount of sleep, study time, and English test score would be our independent variables. So let's go ahead and look at our output for this. Okay, again, we're going to be looking at our assumptions first. So the first assumption we have in our table is our Durbin-Watson statistic, or independence of observations, which we can see is 1.978. So again, our evidence Durbin-Watson statistic, which is 1.978, is between 1 and 3. Again, ideally we want this statistic to be as close to 2 as possible, but anything between 1 and 3 would be acceptable. So we can say that we've met this assumption. Our multicollinearity statistics are going to be important for us this time because we actually have multiple independent variables that we're looking at. So we would find our collinearity statistics over here. And again, for multiple regressions, you guys will always be looking at the final model in the regression. So here we can see we've got tolerance values of 0.999, and we have VIF values of 1.001. Now, usually we say that if tolerance is less than 2, that is a red flag. Okay. So ideally, to meet our assumption, we need tolerance that's greater than 2 and a VIF that's less than 1. Okay, so currently tolerance is less than 2 and our VIF is greater than 5. So even though we've kind of violated our tolerance assumption, we met our VIF assumption, and we also don't have strong correlations or R values that we can see in our correlation table. So I'm going to say that we've met that assumption. Okay. Looking back through our output, we don't have any case-wise diagnostic tables. So because we have no case-wise diagnostic tables, there we go. So that means we don't have any outliers of our dependent variable. So I would say we've met that assumption. The other one we have to look at is normal distribution of residuals, which we can observe by looking at our histogram and our PP plot. Okay, based on our histogram, our data pretty nicely fit this normal curve. Our mean is close to 0, and our standard deviation is in fact close to 1. Based on the PP plot, our dots are fairly lined up along the line. So I would say that given our histogram and PP plot, okay, both of these reflect normal distributions. So I would say we've met that assumption. And then the last one we look at is our homoscedasticity, which is our scatter plot. Again, with the exception of a couple of points out here, for the most part, our data do not show a pattern. So I would say the data appear to be primarily homoscedastic. Oops, primarily, there we go. So I would say we've also met that assumption. right? And some of these are a little bit more subjective in nature. So I grade these with a little bit of leeway, but as long as you provide like the correct evidence in terms of like, oh, if I'm looking at independent observations, I know I need to look at a Durbin-Watson statistic, or if I'm looking at multicollinearity, I should be looking at tolerance and BIF, right? Whether your actual conclusion on if you've met or violated is correct or not, as long as you provided the appropriate evidence in the exam, and I can follow your reasoning as to why you ended up meeting or violating, then you should be good to go and your bases are covered. For the main test, we're actually interested in looking at the regression models. So my first question that I have for you guys is what type of regression method was used? And we can figure this out using the variables entered in remove table. From here, we can see that all of our variables were entered into the first model, and then we started removing variables, right? Variables removed, using a backward criteria. So that tells us that we used a backward elimination method. I then have asked you to identify and interpret the coefficient of determination. So again, this is r squared. So we'll go to our, this is very sensitive scrolling. We'll go to our model summary table where we see our r squared column here. And again, in our class, we always focus on the last model given in the table. So model 2 has an r squared of 0.122. If we multiply this by 100, we can end up interpreting that the predictors, and then we list the variables that were included in the model. So in this case, we can see model B, where the B coefficient is attached to model 2, and that tells us we have a constant, which is our B sub 0. We have study time and English. Okay, so the predictors, study time, and English. I'll specify that this is the English test score because that's what the actual variable is. Those two independent variables account for 12.2% of the variation in writing test score, which is our dependent variable. Okay. Next question in the review is why was the sleep time variable removed from model 1? So we can see it was removed right from model 1 to model 2. We could also see it was removed looking at our model summary. Okay. Now remember, when we use a backward criterion, what's happening is that from one model to the next, we are taking out the variable that decreases r squared the least amount. And then we say if that removal is significant, we would want to keep the variable in because it would be significantly contributing to our prediction of our dependent variable. However, if the r squared change is not significant, then that variable that we removed wasn't really contributing to our model that much. So in this case, we can see that from model 1 to model 2, when we remove sleep time, the p-value for this change statistics was 0.247, which is greater than 0.05, which indicates that when we remove sleep time, we didn't significantly impact the removal, or we didn't significantly impact the change in r squared. However, if we tried removing study time or English score, that's the kind of like the pseudo model that's not included in the output. If we tried removing either one of those variables, the change in f would have been significant. Therefore, we would have needed to put that variable back into the regression equation. So that's why we ended up with a regression equation with just study time and English time. So to answer this question up here, why was sleep time removed? We would say that when, or something similar to, when sleep time was removed from model 1, it did not it did not decrease r squared significantly. And we can back that up using the p-value that was listed in the table, which was 0.247. Okay, so therefore it was kept out of the regression equation. Okay. Next question is asking us to write the regression equation. So again, this is going to be looking at the variables we have included in our coefficients table in the last model. Okay, so our y is our writing score. And we have a constant in our table as 56.581, so that's our y-intercept. Then we add the next variable listed, so which is our English score. So we have 0.266 times some x for English writing score, or not English writing score, for the English test score. So plus 0.266 times some x for the English score. Okay, and then we add our last variable in our model. The b coefficient for that one is 0.121 times some x for study time. What was that? 0.121 times some x for study time. I'll just put study. That sounds fire. Okay. And so that's our regression equation for the prediction of our writing test score. I've then asked you to identify and interpret the p-value in the ANOVA table. So I think that's up here. Okay. Our p-value for our second model is listed as 0.000. If you put 0.000, you will get 0 credit for the question. Okay, because I've told you guys enough times that you should never have a p-value that is equal to 0, right? Instead, p should be less than 0.001 because that is the number of decimal places that we have reported in SPSS, and we have to assume that there is some error in our measurement. So because p is less than 0.001, which we can say is also less than 0.05, which is our alpha, that would tell us to reject the null hypothesis. And our interpretation then would be that, let's do it this way, study time and English test score are significant predictors of writing score, or person's writing test score. Okay. Now the way that we interpret that is slightly different from the way we interpret the p-value for the t-statistic in the coefficients table. So I've also asked you to identify that. And I've specifically asked you to provide the p-value for the t-statistic, or p-value for the t-statistic for English. So if we look at English in our second model, and we look at our p-value here, kind of a similar situation where p is less than 0.001. So we would put p is less than 0.001, which is less than 0.05. So that tells us to reject the null again. And what B is looking at is the slope, or the relationship between the independent and the dependent variable given the regression model that we have, right? So really it's just looking at the linear relationship between the independent variable of interest and the dependent variable. So we could say, as an interpretation, for this p-value, there is a significant linear relationship between English test score and writing score. All right, and that is our example for our multiple regression.